This circuit you see here has the ability to capture energy from its surroundings. The energy exists in the form of radio frequency signals from cellular towers, Wi-Fi signals, and other sources. It then converts that energy into electricity and stores it in these capacitors, the orange ones you see here. This is completely accurate, and I will demonstrate everything practically in this video. Right now I have set my multimeter to DC voltage measurement mode and it is currently at 0. Now I will connect this circuit to my meter pinouts where the red is positive and black is negative. You can observe that the voltage is gradually increasing even though no external power source is connected. How is this happening? This is because the point you see here is acting as an antenna, absorbing radio frequencies from the surroundings, converting them into electricity, and storing the charge in these capacitors as DC voltage. Currently, you can see that the charging is happening in millivolts, which is quite low. At this moment, we have managed to charge it to around 12 millivolts. Now we need a larger antenna. Since my body is also a conductor, it will function as an antenna as well. Let me touch it and observe the change. Now the voltage is rising rapidly. We have already exceeded 160 volts DC. This increase happens because the antenna generated also depends on the number of nearby cellular towers and how close they are to this device. At this point, we have reached around 400 millivolts. Let's continue observing and see the maximum voltage it attains. Now, we have reached approximately 6 volts, and the voltage is still rising. It seems like reaching 1 volt is quite close. Also, some voltage is lost across these diodes because multiple diodes are connected in series. However, these diodes are essential for converting AC signals into DC. At this stage, the charging rate has slowed down significantly. Initially, I expected the voltage to at least reach 1 volt. As you can see, it is currently at 889 millivolts, and now it has started increasing again. Finally, we have crossed the 1 volt mark, and it is continuing to rise. Now, I will remove my hand, and you should observe the voltage drop. You can see that the voltage is quickly decreasing as soon as I remove my fingers. If I reconnect my fingers, the voltage starts rising once again. Here you can see my camera stand, and at the bottom there is some cardboard which is used to isolate the tripod from the ground. This tripod will act as an antenna. There's a wire here with one end having a clip while the other end is bare. I will connect the clip end to the tripod to function as an antenna while the bare end will be connected to the circuit. At this moment the meter is displaying 0 volts DC. I will now connect the antenna wire, but before that let's first connect these wires. Right now it is showing 53 millivolts. Let's discharge it first. As soon as I disconnect the wire, the circuit will start recharging from 0. Now the wire is disconnected and the capacitors have already started charging. The voltage has reached 10.8 millivolts and is still increasing. Now let's connect the antenna wire and observe the effect.
As expected, there is a sudden increase in the charging voltage. Let's monitor the highest voltage we can achieve here. Interestingly, when I touch the wires, the voltage increases significantly. I'm not entirely sure why this is happening, but it is certainly fascinating. The voltage has now increased to around 1.7 volts, and the charging speed is quite fast. We are approaching 2 volts, which is really exciting. Now I will remove my fingers, and you can see that the voltage is dropping again. Initially, I thought that a loose connection might be causing this, but now I suspect something else is happening when I touch the circuit.
Let's see how high the voltage can reach. We are very close to 2.5 volts. Wow, now we have reached 3.5 volts. If I remove my fingers, the circuit starts discharging again. Something is definitely happening when I touch the wire. Oh, now I understand. My body is acting as a connection to the ground. When I touch the wire, the circuit is receiving an AC signal from the surroundings, and my body provides a grounding effect. This allows the capacitor to charge faster by completing the circuit. This also means that if you plan to use this type of circuit, you will need a proper ground connection.
Now it seems like the voltage is stabilizing at around 4.5 volts. Let's try a small experiment. I have connected a tiny buzzer to the circuit. The current voltage reading on the meter is 460 millivolts. One noticeable thing is that without a ground wire, the capacitors do not charge efficiently. Once again, I will use my body as a ground connection, just like before, and observe the impact. You can see a significant increase in voltage. It has now reached around 1.8 volts.
Now, I will connect the positive wire to the buzzer and bring my microphone closer so that you can hear the sound. Here it is. This time, the voltage is slightly higher. We are still at 4.5 volts. Let me try connecting it again and listen to the sound. Notice how the voltage drops significantly when the buzzer is activated. If I keep it connected, the voltage does not increase. However, when I disconnect it, the voltage starts rising again. Let's wait and allow it to charge before connecting the buzzer again. Next, I have connected a small green LED to the circuit. Once again, I will charge the capacitors using my body as the ground connection. Let's test the LED now. I think that's enough charge. I will now touch the clip to the circuit. There it is, a brief blink of the LED. Let me repeat it so that you can see it again. This time, pay attention to the voltage drop on the meter. As you can see, the voltage dropped to 1.945 volts. Now, the LED is not glowing at all. At 2 volts, the LED should be glowing, but the voltage is not high enough. Oh wait, there is a slight glow. This time, I will not disconnect the LED wires. Instead, I will simply touch my hand to the circuit. Now you can see that the LED is glowing slightly. It is emitting a dim light, but it is working. Let me try touching another part of the circuit. Yes, the effect is the same. As you saw, this circuit produced around 4.5 volts, which is quite decent. Some of you might be wondering if this means we can charge a smartphone, since most smartphones charge at around the same voltage. Unfortunately, the answer is no. The current produced by this circuit is extremely low, making it unsuitable for powering devices like mobile phones. Now, let's discuss the reason I made this video. Many of you may have heard of Maxwell Chikumbutso. He claims to have created a device that can capture energy from radio frequency waves and convert it into usable electricity. According to him, his device can generate about 0.5 megawatt of power. However, based on my research, I find this claim difficult to believe. The setup required to achieve such power levels would be highly impractical. This small circuit here barely generates milliwatts, so you can imagine how challenging it would be to scale it up. Another claim he makes is that he built an electric car that never needs charging and runs indefinitely on radio waves. Again, this is highly improbable. Without a proper ground connection, generating sufficient power for an entire car seems impossible. The setup would have to be enormous, possibly larger than the car itself, and it would still depend on the type of cellular towers in the area. While this circuit is not particularly practical for generating useful power, it does offer an interesting way to capture free energy. However, calling it a free energy source is misleading, as it merely converts existing radio frequency waves into electricity. As for Maxwell Chikumbutso's inventions, they have not been approved for patents, likely because they resemble perpetual motion machines, which are scientifically unfeasible. His house, as per my research, still uses standard electricity, and he pays his bills just like everyone else. That's all for this video. See you next time.